today I do my last lecture. Yeah, so I want to do one thing first. So the idea, there is a motto that I want to mention, that is, you have seen a lot of representation theory of finite groups, and the motto is representations theory of compact groups is a lot like finite groups, for finite groups. Right? So what have you seen for finite groups? You have finite dimensional irreducible representations. Every representation is a direct sum of irreducible ones, and you study them by their characters. And the same is true for compact groups. So, so as an example, let us do a character table for the group SU2. And then tomorrow in the training session you will do SO3. Yeah? So what do we have to know to do the character table of a group? I think two things. Because in one direction we put conjugacy classes. They were in a row, I think. And in the vertically we have the irreducible representations, right? So let's do the easiest thing first, right? So the irreducible representations, I think we had these things. We do polynomials in two variables, and then homogeneous of some degree d. And d is an integer that is at least 0, right? And we had an action of this group on that. And also tomorrow you will, in the training session, compute that action in a very detailed way, right? And the dimension of this thing is d plus 1, right? Because you start with x to the d times y to the 0, x to the d minus 1 times y, up to y to the d, that is d plus 1 elements. Okay, so those are the irreducible representations. Now the conjugacy classes. So then we have to say, what do we do with an element in SU2, right? So let's say G is A, B minus B bar, A bar, B in SU2. So the elements look like this. What can we do? Well, this is a unitary matrix, and you could try to diagonalize it, right? It has two, so can be diagonalized. This you learned in the linear algebra course. Diagonalized. So the fact that it preserves the inner product means that if you have one eigenvector, then you take the perpendicular to that, and that is another eigenspace, and it is the direct sum of the two spaces. So that always works. And what can you say about the eigenvalues? Eigenvalues, so for a unitary matrix, the eigenvalues are e to the I phi and e to the minus I phi, because the determinant of the matrix is the product of the two eigenvalues, but the S here means that the determinant is 1. Oh, yeah, they look like this, and there is this thing that A absolute value squared plus B absolute value squared is 1, right? That is the only equation that you need for SU2. Okay, and this phi, say e to the I phi, is in the circle, in the complex numbers, maybe in the multiplicative group of complex numbers, and you could say that you take, well, doesn't matter. Let's just leave it like this. So everybody can be diagonalized. So we can say that we map S1 into SU2 by mapping e to the I phi. Now I need e to the I phi goes to this matrix, e to the I phi 0, 0, e to the minus I phi. So this embedding, this circle embedded in the group meets all the conjugacy classes, that's for sure. But how often does it meet a conjugacy class? So what is the intersection of a conjugacy class with this circle? Well, that has to do with the following thing. When I make this matrix, I could say like this. I have this G, it has two eigenvalues. If there are only two exceptions to that, you could have a double eigenvalue if the phi is 0 or pi, right? Then this matrix is the identity or minus the identity. But in other cases, there are two distinct eigenvalues. And you have to, when you write a matrix, you have to number them. And there are two possibilities to number them. One is the first one, one is the second one. But if you could as well have, so what I say is when you do this, you number the eigenvalues, you take eigenvectors in these eigenspaces, and that is your orthonormal basis. Then that basis will differ from the standard basis by a unitary matrix, not necessarily of determinant 1, but you can scale your eigenvectors to change the determinant. And then your basis of eigenvectors differs from the standard basis by an element of SU2. And that means that the matrix that you will get by doing that, so the G is conjugated by an element of SU2 to this. But I made a choice of numbering of the eigenvectors, or of the eigenvalues. And if I choose the other numbering, I get, but I would say e to the minus I phi 0, 0, e to the I phi is conjugated to e to the I phi 0, 0, e to the minus I phi. And I think by this matrix 0, 1, minus 1, 0, right? This is an element in SU2, and it conjugates these two things. Right? This one also has determinant 1, so it is okay. Yeah? So what I now want to write is I want to make a bit visible the set of conjugacy classes. So this and this should be mapped. They are the same conjugacy class. And how can I make a set of conjugacy classes? Well, I can take the trace of my matrix. If I take the trace of a matrix like this, I get A plus A bar, right? But the A, well, actually it's easier to look at the eigenvalues. I get e to the I phi plus e to the minus I phi. This is 2 times the cosine of phi, right? So I go to the interval from -2 to 2, right? This is what the trace brings me to. And on this circle, what does that map do? It sends the trace of this thing, this is 2 times the cosine of phi, right? So this is the set of conjugacy classes. Okay? Okay, well then we are ready for our character table, right? So here I make it, hop. Well, I don't need to go that far. Here I have the elements -2 to 2, right? And this is the set of cosine of phi, where phi, well, e to the I phi, G, is in the circle, okay? Okay, and here I have my irreducible representation, so I just write C, X, Y, D, where D is greater or equal than 0, okay? And now I have to write the character. And that is the character, yeah, so when you want to write the character of a irreducible representation, you are free to choose any element in the given conjugacy class, right? So which element should we take? I think we take this one, right? The one that that is diagonal. Because what does that do? This e to the I phi, 0, 0, e to the minus I phi, it maps x to e to the I phi times x, and y goes to e to the minus I phi times y. And so if I look at, maybe I should write here, x to the y, no, x to the a, what should I write? J and k, right? X to the j, y to the k goes under this e to the I phi matrix, goes to e to the I phi x to the j times e to the minus I phi times y to the k, and this is the same as e to the I phi, and now I get j minus k times x to the j, y to the k, right? And for example, well, when I do this cxy homogeneous degree d, my character, first let us take x to the d, this goes, then so this x to the, so my basis, this is the point, if I take the basis of monomials, then they are eigenvectors for this operation, right? You see, if I act with this element on this, it is brought to itself with this vector. And so to get the trace of my group element for this representation, I just have to sum these things over the j and k such that the sum is d, right? So I could write sum j plus k equals d, and I think that j should be greater or equal 0 and k should be greater or equal 0, and then I get e to the I phi j minus k, right? Is it visible? And this, so you could say this is e to the I phi times d plus e to the I phi times d minus 2 plus e to the I phi times minus d, right? You just go down like that. Yeah? And then, well, if you are a little bit into making a simple yeah, what you can make one expression for this, right? I think this is e to the I phi times d plus 1 minus, is it true that you get, well, let me see, maybe I should e to the I phi minus d plus 1, right? Well, minus this, okay, times, divided by e to the I phi minus e to the minus I phi, right? If you know x to the something minus y to the same power divided by x minus y is a sum, and it's this, right? And so this is also, I think this is also the same as the sine of d plus 1 phi divided by the sine of phi, right? Yeah? Yeah? I get approval? So this is my character table, right? I mean, here is instead of finitely many conjugacy classes, I have a whole interval of them, a continuum, but the irreducible representations are just countably many, not finitely many, but countably. D equals 0, 1, 2, 3, 4, and so on, right? So that is the character table, and tomorrow you will make a character table for SO3. Okay. This is physical work. Let me try. This one is the same. Just as difficult. Okay, so let me continue talking. So, for what we want to do, these characters are not helping too much. We need more. We wanted to do Fourier analysis on the group and on the two-sphere, so we need not only functions that are constant on conjugacy classes, we need all the functions that come from representations. We need so-called matrix coefficients. So that's what I want to say. So we need our goal, Fourier analysis on SU2, well, on S2. So class, yeah, not only functions, that are constant or invariant under conjugation. So now I am going to look at this little paper I have. So we need all matrix coefficients of, say, G in SU2 acting on C, X, Y, D. And not only this, we need all these coefficients with respect to an orthonormal basis of this C, X, Y, D. With respect, yeah, sorry, I repeat this. When you want to do orthonormal, you need an inner product on this representation. And I need an inner product to an inner product that is invariant under the action under SU2, under this action. So we need all this. And now, so I think I have now 20 minutes, no, half an hour left, right? So let's see how far we can go. We need that because what does that give us? I think some general theory was shown by Intan the previous time. So Intan, she showed us, well, she was almost finished. So now, so let's say this is pages 16 to 17 of this bachelor thesis of this Bentham guy. So you can look it up there. So if V and V prime are irreducible representations of G, and now G is any compact Lie group, and you have U and V in the V, and U prime, V prime in V prime, and you have invariant inner products, and denotes a G invariant inner product on V and also on V prime. I use the same notation for these inner products. Okay, so then you have a formula, if then, right? That makes sense. You have this formula that the integral over the g and g of the g acting on u and then inner product v times g acting on u prime inner product v prime. These are numbers, these are complex numbers, right? And you have to integrate it over the group. So what you need is a kind of volume form on that group. And people call that Haar measure. Mu g is the invariant measure. And I think we don't go into that. Okay. This is the analog of, if for the finite groups you would do this. You would sum over the g and g some expression, the same expression, without the mu, and then you would divide by 1 over the cardinality of the group, right? That is the analog. So when you generalize from finite groups to compact groups, a summation over the group has to be replaced by an integral over the group. And you put the measure there. Okay, and this integral is 0 if v is not isomorphic to v prime. And so there are two cases. Either if you have two irreducible representations, they are isomorphic or they are not. And if they are isomorphic, you can as well assume that they are the same. So, and what comes out if they are the same? Then you have u inner product u prime times v inner product v prime divided by the dimension of v if v is equal to v prime. Okay, I hope that this is what was done yesterday when I was away. And how should we see this, right? These functions are functions, this is a function of g, this is a function of g, because the u and the v and the u prime v prime are fixed. And so these are elements, yeah, they are functions on g. And what does this relation say? Suppose that v is not isomorphic to v prime, then this says that these two functions are orthogonal in the space of all functions, because the inner product, I don't know if we have talked about that already, but you can look at for f and g, say continuous f1 and f2 is better, as g denotes an element of the group. So for f1 and f2, continuous functions on g, we define the inner product of f1 and f2 to be the integral over g and g, f1 of g times f2 of g bar times the mu of g. And this again, you are used to this for finite groups, because then you would sum over the group the first function times the complex conjugate of the other one and divide by the number of elements of the group, right? That was the inner product of these characters, for example. So here you do this, except that these are arbitrary continuous functions. So you see this is an orthogonality relation. If v is not isomorphic to v prime, then this is always 0, no matter how you take the u and the u prime and the v and the v prime. But if they are the same, then you get this. So actually, what I want to say is that now we can make an orthonormal set of functions on this group, right? So actually, continuous functions on g, we could say these are elements of C of g, and now here the C stands for continuous, and this is contradictory notation as what I have seen with the finite groups, because their C of g was the set of class functions. So let me say C0 or so for continuous, yeah? That there is... Oh, that was a complex number. Okay, so then it's fine. The C with no blackboard bold is just continuous. Okay. So so this makes us, we can make, oh. Yeah, we are going to make a maximal, well, an orthonormal set of functions, and claiming that it is maximal orthonormal, so that it is what is called a Hilbert basis of the completion of this space of continuous functions with respect to the L2 norm. And it doesn't matter, actually. I'm only interested in these functions and not in generalities about Hilbert spaces. I want to get the right basis of functions to work with. So, so now I would like to say this. I just erased my character table, but we have these representations here, and I want orthonormal basis for them, right? So let's say that first a bit of theory. If u d comma 1 up to u d comma d plus 1 is an orthonormal basis for C, X, Y, index D, right? And the inner product, I still have to tell you what it should be. So that is an interesting thing in itself. Then the functions and which functions are they? They say, well, they are square root of d plus 1. The square root is there because here is a division by the dimension. And you see that I want inner products to be 1 and not 1 over this. So I scale the functions with that. Okay. So let me see. Times f d I or ij, and they send an element of the group SU2 to the square root of d plus 1 times g ui inner product uj, right? So this, by the orthogonality statement there, then this is an orthonormal set. Then the function sub form an orthonormal set in the space of continuous functions on my group SU2. In the continuous functions on SU2. Right? That is the... And now, what is such a function here? What does that do? If you have this is the ith function, the ith element of my basis. So I claim that this is the same as, say, the rho d of G, where rho d means I take the matrix of my of this element G acting on this space, on this CXYD with respect to this matrix of the UIs, right? Then this is the coefficient, this is the JI coefficient, right? Because I'm in the, so the ith column of this matrix is what the image is of this basis vector. And to take the jth coefficient, jth coordinate of that column, I take the inner product with uj. Right? So you can say, that is why these functions are called matrix coefficients. You can write them either with your inner product, but use that this is an orthonormal basis for the space. And you can also say, well, it's these matrix coefficients, right? The ji matrix coefficient coefficient of G in the representation C, X, Y, D. Okay, that is what these functions. So you get from representation theory, you get an orthonormal set in this set of functions on SU2. But our goal was to do S2. So that's not the same. Actually, if you want, I think it was on the board a moment ago. If I write elements of SU2 as these matrices A, B, minus B bar, A bar, then we can view SU2 actually as the free sphere in R to the 4. So actually, if my ambition had been to do Fourier analysis on the free sphere, I would be much closer to my goal. But no, my goal was to do S2. So now I have to work, right? So now we must go, how to go to S2, right? Well, one ingredient, so the first step in this, is to go from SU2 to SO3. And that was also explained yesterday, and let me mention it again. SU2 is contained, so I think SU2 is the elements X in the, what was the notation, I think, right? It is the quaternions here, quaternions, not the upper half plane, such that the norm of X is equal to 1. And X is, maybe I should recall, this quaternions, this is R times 1, direct sum R times I, direct sum R times J, direct sum R times K, right? And these ij, oh, maybe small ijk is better. Well, no matter, doesn't matter. We do this, right? It is in the lecture notes that you know what these things are. You send an X here, goes to the matrix of conjugation by X. So on the space, on V, and this space is R times, it is the imaginary quaternions. So there are 3 that these ijk, there are these 3, these are the ones that I want. And the matrix of conjugation by this with respect to the basis ijk. Okay? Let's do that. Right? And the claim is if I do conjugation by X, then the one element is mapped to itself. There is an inner product on the quaternions for which the orthogonal complement of 1 is this thing. And so this is sent to itself. And then you get a 3 by 3 orthogonal matrix. It is this thing. And the kernel of this, you will also do that tomorrow in the training session. The kernel is the set of matrices identity and minus identity. That's the kernel of this map. And this map is surjective. So the first step is to pass from the group SU2 to the group SO3. Okay? And the representations of SO3, we get them for free now, because if you have any representation of SO3, you can compose with this map and you get a representation of SU2. So the only thing we have to do is to find out which irreducible representations of SU2 are trivial on the element -1. And that is very quick to answer, because that element -1 is the minus identity matrix here, and it sends x to -x and y to -y, and so it is only when my monomials are of even degree that this is scaled by the factor 1. If my monomial is of odd degree, then it goes to minus that monomial. So I'm saying that I know the irreducible representations of SO3. Somehow we found out what they are by going to a lower dimensional group, say SU2 is only 2 by 2 matrices, but complex. And it was not so hard to find the irreducible representations of that. So the irreducible representations of SO3 viewed as irreducible representations, well, they are automatically irreducible then, representations of SU2 are the CXYD with the odd, right? I think, yeah? That's a bit strange. No, with D even, and then the dimension is odd. With D even. So we have C times this, then we have C times x squared, direct sum C times xy, direct sum C times y squared, and so on. This is dimension 1, this is dimension 3, then the next one will have dimension 5, 7, all the odd numbers appear. Okay? Because, as I say again, if you send x to -x and y to -y, then these monomials are fixed, right? So that means that as a representation of SU2, this homomorphism from SU2 to the 3 by 3 matrices on this space has -1 in the kernel, so it factors through this quotient of SU2, right? So then it gives me a representation of SO3. Okay, so we know the irreducible representations, and we can so that is the first step. We need this inner product, so let me explain about the inner product. So SU2 invariant inner product on CXYD. So how do I do that? So if you have, suppose I have F for F and G, no, F1 and F2, I should say, do that. In CXYD, say, we view F1 and F2 as polynomial functions on C2, right? Because we can, for example, to make it completely clear, x sends a point a comma x in the point a comma b is the x coordinate, so this is a, and y in the point a comma b is b, right? And then every polynomial is a function on C2, okay? Just like you did before you learned about polynomials. You only have to forget. Okay, so polynomial functions on C2, and then we can define F1 inner product F2 will be the integral of F1, say, V times F2 of V bar, and here I do mu S3, here over the set of V in C2, such that the norm squared, the norm of V is equal to 1, right? So as we, maybe I should put everything away now. There is nothing to see there. So we have to make a number with this F1, F2. We have to do some bilinear form. And it should be invariant under the action of SU2. But SU2 is unitary transformations of C2, so it maps the unit sphere to itself, right? So if I sum all the values of this product over the unit sphere, I get something that is invariant under the action of SU2. Right? I mean, this integral, yeah. So what I do, this is the volume form, the usual volume form on S3. If you go back to your first year calculus, and they tell you integrate this function on the 3 sphere, then you would do this. This is what you would do. So you could express that in some kind of spherical coordinates, but I don't want to waste my blackboard space and my time. So this is usual, as in usual calculus, as usual, right? So that is the inner product on the that we take. It has the right requirement, and then the question is, what is my orthonormal basis then, right? So orthonormal basis, and here for this inner product, now I need to look up what comes out because I can't remember that. So here, wow, why did I not copy that? Okay. Ooh. Yeah, okay. We scale it like that. Okay, so it is on page 19 of the lecture notes there. It is that you get x to the j, y to the d minus j times a factor, and this factor is 1 over, 1 over pi times the square root of, yeah, no, this is, I should take more space. Okay, I do it again. And I start from the beginning. It is 1 over pi times the square root of d over j, so binomial coefficient, times, oh, just to the power d plus 1 over 2, right? This is quite incredible, such a number, but it happens. And this is only a number. It has to go to x to the j, y to the d minus j, right? So this is one of the monomials in my basis, and it was orthogonal already, so that is nice, but this is not surprising, because the diagonal matrices in SU2 were just scaling this x and this y by factors e to the I phi to the something. So these are eigenvectors, and you know eigenvectors with different eigenvalues are orthogonal anyway. So, but the question is, which factor do you have to put to make it really orthonormal, to give it norm 1? And this Bruin-Bentham says that he did not do the integral, because you have to do this integral to find out what, but he asked it to the computer algebra system Maple. Maple, yeah. So computer algebra systems can do this for you. not only in million specific cases, but also as the j and the d as parameters. It's quite impressive, right? So we don't need to do that. So this is an orthonormal basis, right? If you let this, so here you can say 0 less or equal j less or equal d. That is an orthonormal basis of this representation that we have. Okay, that is the second step. Then we have to make a third step. And I have 5 minutes. Okay. So we have to go from SO3 to this S2. Yeah, thank you. Yeah, So step 3. So here is the two-sphere. And this, what is this called? North Pole, right? The North Pole. And this is our base point on the two-sphere. So we make a map from SO3 to S2 by sending an element G to G times the North Pole. Now, if you want to do this matrix multiplication, then maybe you should write the North Pole as the vector 0, 0, 1, right? Yeah? So this is a... Yeah, this is nice because this is not, this will be a surjective map, right? Because you can, if you can do rotations over arbitrary axes, over arbitrary elements of SO3, you can make this North Pole go to any point on the sphere. And I claim that well, what is the stabilizer of the North Pole? It has stabilizer these matrices, right? I think cosine phi, sine phi, minus sine phi, cosine phi, and then a 0, no, a 1 of course. Here you have zeros, but this is a 3 by 3 matrix, even though there is little room. Yeah, those are the rotations about the z-axis, and they fix the North Pole, right? And this is also a circle group. It is the set of these things, and that is also the circle group S1, right? It is again phi, an angle. So actually, this is also G times, say, rho, if I call this rotation over phi about the z-axis, G times rotation over phi about the z-axis times n. That's the same thing for every phi, because this thing stabilizes n. But that means that this map factors through this quotient, right? Because, and this quotient, don't think that it is a group. Is not a group, because this S1 is not a normal subgroup, not a group, but you can view it as a manifold with a transitive SO3 action, right? Because the SO3 acts by multiplication on the left, right? So I take, this is the set of cosets, say, group element times this subgroup, but I can still multiply on the left by group elements that permute these cosets, right? And as a set with an SO3 action, this one is isomorphic to that one. So that makes a relation between the two-sphere and group theory, right? And on the group, I can do all my things. So I can say, well, then the continuous functions on S2, I can also say that is the same as continuous functions on SO3 that are invariant under this action. So I put S1 here to say invariant, oh, there is a 1 as a superscript, I think, invariant functions, so invariant under right multiplication by these rotations, right? Rotation over phi around the z-axis. So it means functions on SO3 such that f at x is also f at x times such a rotation for all x and for all these rotations. And so, happily, I chose everything so that these functions are eigenfunctions for this action of this S1. So my basis, my orthonormal basis, consists of eigenfunctions for this for S1. For this S1, I mean, if you choose all the things a bit right, then it is like that. And then, so I just take the ones with eigenvalue 1, right? And that means that you have to take, well, this scales with e to the I phi to the j, and this scales with I phi, e to the I phi to the j, d minus j, with a minus also. So they have to be equal, right? So you have to take j is d over 2. And now we're happy that d was even, because then you have x to the d over 2 times y to the d over 2. So those are the ones that give you the basis here. And let me just give you the outcome, the final result of these functions, because that is normally I don't like formulas too much, but in this time, I mean, it is so much my goal to make these functions that it is worthwhile to write them down. So you find the usual spherical harmonic functions that you find in tables, for example, in books on quantum mechanics, where they do the hydrogen atom, because there the SO3 group gives the symmetries. So you have functions, so you have functions y, l, j. Now actually, the L is something like d over 2 or so, I think. L is d over 2. So it comes from my representation Cxyd. And this at the point P, theta, comma, phi. So this is a point on the sphere with spherical coordinates theta, phi. You know how that works, so you could write it out. This is, now comes the whole thing, square root of 2l plus 1. You see, this L is really d over 2 times 2l, choose L, to the power of a half, times 2l over j, times a half, minus a half, sorry, times e to the I phi times j minus L, and I'm not yet finished. Oh, now comes it doesn't even fit. I continue here. Times the sum. Yeah, this is really bad. Huh? 0 less or equal n and m less or equal L, and n plus m is j. I cannot, yeah. And then there is more binomial coefficients. L over L choose n, L choose m. And now comes something like cosine of theta over 2 to the power n plus L minus m times I times the sine of theta over 2 to the power m plus L minus n. And now I can end. And here I should say that this L is in n. So maybe where does the index go? And 0 less or equal j less or equal to L. That is how you can take the indices. And if you take all these functions, they are precisely what you need to do Fourier analysis on the sphere. And even these are eigenfunctions for rotations about the z-axis, right? So they are made for measurements by physicists of what you call energy and angular momentum of the hydrogen atom when you put your magnetic field in the z direction. Okay, thank you.